Compiler construction number 6. All right, recall that last time we introduced the register allocation problem where we have to look at our instructions, figure out what variables they use that to figure out when two variables conflict or interfere. Then we use that to construct a graph called the interference graph, which we're going to use to figure out what exactly we should do. So let's just draw our interference graph again. So this is the graph I, and so we have V, W, Z over here, X, and Y. Then we also have T, our temporary variable, and then the RAX register. Then we also have the move graph, which has the same nodes. You know, if I had like multiple colors, probably what I would do is I would overlay the graphs on top of one another. But yeah, we don't have that. Okay, so here are two graphs. Now we have V is connected to W, W is connected to Y, W is connected to Z, W is connected to X, and then also X is connected to Y, and Y is connected to Z, and then Z is connected to T, which is connected to RAX. Now our move graph, we have Y is connected to X, Y is connected to T, there. X is connected to Z, Z is connected to RAX, and then V is connected to X as well. Okay, so here's our graph right here. All right. Now, what is it that we want to do? Ultimately, what we want to figure out is how we can assign each one of these vertices right here to a different register. Now, the way to think about this is, actually, you know what? Let me just pause 1 second. This graph right here, like, what data structure should you use? There's basically sort of like two techniques for representing graphs. There are adjacency matrices and adjacency lists. And maybe there's one more, which is objects and pointers. So here's what an adjacency matrix is. An adjacency matrix would be to build a matrix that had all the nodes on as the rows and columns. So we'd have like V, W, X, Y, Z, T, RAX, and then we'd have V, W, X, Y, T, Y, Z, T, RAX here. And then like right here, since there's a V to W, we would go and we'd say, okay, V is connected to W, right there. This is going to be a symmetric graph, by the way. So it could be like that. And then like W is connected to Z, so we'd have a W in the Z column right there, and W and Z. We'd have this big thing. That's one way to do it. Another way to do it is to just store the edges. So this is the matrix. This is the edge list. And the edge list would basically say that we have V and W in the graph, and then we have W and Z in the graph, and we have Z and T in the graph, and so on. We would list them all out. Finally, the other way is the object and pointer value, where we would basically say that like associated with V is a list of all its neighbors, which would be W. And then W would have a list of its neighbors, which would be V, Y, X, and Z and X. Then we would say like Y, we would list out its neighbors, which would be W, Z, and X, and then so on. Okay, now there's a lot of ways that you can do it. My personal thing that I find the most convenient are these graphs right here. Yeah, but you know, do whatever works for you. Okay. So now, and none of the algorithms that we talk about, like, it's not really, no particular technique is better than any other for representation. Okay, so now we have to phrase we're going to phrase the thing that we care about, which is register allocation, in terms of a pre-existing graph problem. And here's the graph problem. What we're going to do is we're going to imagine that we have an infinite number of colors. And we want to label each point, each vertex, with a color such that no vertex is adjacent to something of the same color. For an analogy, you can think of this as being like taking a map. And what you want to do is, so the map has like all the political territories of the world on it. And you want to use like red, green, blue, teal, etc. You want to color in all of the countries. But obviously if two countries share a border, then they can't have the same color because then you won't be able to tell where one country starts and the other country ends. So every country has to have a different, whenever two countries are next to one another, whenever they share a border, they have to have different colors. Now, obviously, you could use 195 or whatever colors for all the different countries in the world. But of course, like, it's okay for like America and Japan to have the same color since they're not adjacent to one another. So rather than just thinking about like what is the most number of colors you could use, which of course is the same number of vertices, what we're really interested in is the smallest number of colors. Okay, now as an aside, you may know this, that if the graph is planar, which basically means that it can be like written flat without any overlapping edges. So for instance, like see this edge right here, it overlaps. Well, it turns out we can actually draw this by drawing a Y all around there. And then there wouldn't be an overlapping or like this. So if you can draw your graph without any edges overlapping, then it's planar. And if a graph is planar, then you know that you'll be able to use 4 colors to you can color every planar graph with 4 colors. This is the so-called 4-color theorem. Anyways, we have 13 colors, but we kind of actually have more than that actually, because we have 13 colors for all the registers, plus we have all the stack locations. So really what we want to do is we want to write an algorithm that figures out a coloring. And when it figures out a coloring, what we then do is we're going to take the colors and we're going to like number them from 0 to infinity or whatever. And the first 13 of them, those ones are going to be registers, but all the other ones aren't. And those other ones will be stack locations. Okay. Now, this graph coloring problem is actually extremely similar to what you're doing when you play Sudoku. So when you play Sudoku, essentially the idea is that, like, in Sudoku, the Sudoku graph, so a Sudoku board is a graph, because if we think about like the edges, like the column, the rows, it's like all those, each individual point on the graph on the Sudoku board is like a different node. And then all the ones that are on the same row, they have edges connecting one another. And all the ones that are in the same column, they have ones connecting. All the ones that are in the same house, they have ones connecting. And so basically, every single time you play Sudoku, you are given the exact same graph. But that graph has an initial coloring. And what we mean by an initial coloring is that it starts off with some vertices previously labeled as 1 through 9. And then what your job is you're trying to figure out how to color all the other vertices, the ones that don't initially have labels. And so when you play Sudoku, you are doing graph coloring. It's just you're coloring a particular graph over and over and over again with different initial coloring layouts. And the colors are always 1 through 9. Okay, so that's good. So we know that this one is going to be able to be colored with 4 vertices, with 4 colors. So let's just like assume that we're going to use that many, and that'll simplify the explanation. We'll flip back to the move biasing graph in a moment, by the way. Okay, so here's what we're going to do. I'm going to write 6.2 right here. And what we'll do is we're going to like execute the algorithm ourselves and then we'll go back and we'll like write out the algorithm. So what I'm going to do is I'm going to copy this so we can have multiple copies of it. Okay, we'll put it right here. Okay. All right. Now I'm going to add in additional vertices for the registers that we know we're going to use. So we're going to have another one for RBX. We're going to have one for RCX. And we're going to have one for RDX. These are the 4 general purpose registers that have been around since there were only 8 registers. Okay, then what we're going to do is we're going to do an initial labeling of these ones. We're going to label this one 0, this one 1, this one 2, and this one 3. So what this is an initial coloring of this graph. Now what we're going to do is we're going to go through and we're going to basically apply like the Sudoku algorithm to color this. So think of it like this. Right now we know that this one is labeled with a 0. So that means that t can't be 0. So what we're going to do is we're going to assign t the lowest number that we possibly can, that is possibly allowed to be. So we can't label it 0, but we could label it 1. So we'll put a 1 right here. Okay, now let's go over to this one, and we want to label z with the lowest number that we can. We're not allowed to label it 1 because it's adjacent to 1, but we are allowed to label it 0. Also, if we look at our move graph, we see that z is connected to RAX. So that means that we should prefer, if there were ties, to label it with the same color as that. So what do I mean by this? So z, we are allowed to label it 0, 2, or 3. And so because we are allowed to label it 0, 2, or 3, we have to like break the tie somehow. And what we're going to do is we're going to break the tie by looking at the move graph. And if z is related to something that already has a color, then we're going to choose that color from when we break ties. So in that case, we're going to label z as 0. Okay, now let's go to the next one. Let's go to w. So w is not allowed to be 0 because that's adjacent to z. So let's give it the label 1. Actually, okay, I'm running the algorithm in my head, and if I let w be 1, then it's going to make it so I can't let y be 1. And I want y to be 1 because I want it to have the same color as t because they're related in the move graph. So I'm actually going to not look at w right now. I'm going to choose y next. I'm going to choose that one and label it as 1. I can give it the label 1 because it's only adjacent to 0 right now among the things that have already been assigned. And so that means I can't use 0, but I could use 1, 2, or 3. And then among all those, I'm going to choose the one that is related to in the move graph, because the move graph says that it's connected to t, which already has 1. All right, so now I can look at w or x. So let's look at w. So w is not allowed to be 0, and it's not allowed to be 1. So that means the lowest number that it can be is 2, or it can be 2 or 3. The lowest number of those is 2, and it's not connected to anything in the move graph, so we'll do a 2 right here. Now let's look at x. So x is not allowed to be 2 or 1, which means that it can be 0 or 3. And it is related to z in the move graph, so we would prefer labeling it as 0. Now we look at v. And v is not allowed to be 2, which means it's allowed to be 0, 1, and 3. And notice that it's related to x, so we should prefer giving it the label 0. So we just did it. We just came up with a labeling of this graph. Now, what's like the impact of doing that? Again, like I said, we're going to run the whole algorithm. And I really should have copied this first. So what I'm going to do is I'm going to go back to the notes to day 5, and then we'll go back and we'll copy this program right here. Okay, so here's what we're going to do. We're going to copy here. Okay, it's we're gonna, there we go. Copy this up here. All right, copy that. Now we'll go back to the class we're on, number 6. And then, you know what I'll do? I'll paste it down here. Okay, so you know what I'm going to do? I'm going to paste it again. All right, so now I got 2 copies of it. I'm going to adjust the screen real fast to move down. Okay, so now you have the PDF, so you can look at the full version of the screen. But what I'm going to look at is I'm going to have, you know, the graph up above. And what we're going to do is I'm going to go through and I'm going to erase all of the variables from here. And then we're going to replace those variables with the register assignments that we just made. And then we'll know which ones, which variables it's supposed to be by looking at the other side. All right. Okay. So the first thing that we have is V, which we've assigned to RAX. So we'll change this to RAX. Then we have W, which we've assigned to number 2, which is RCX. Then we have V, which is RAX, and X, which we have assigned also to RAX. And since those 2 are the same, we'll be able to cross this instruction off and get rid of it, because it's a move from just one thing back to itself. Then we replace X right here with RAX. Then we have moving X, which is RAX, into where Y is, and Y is RBX. Then we have another Y of RBX. Then we have X, which is RAX. And we're moving that into Z, which is also RAX. So we'll be able to get rid of that as well. Then we have an add Q of W, which is RCX. And Z, which is RAX. Then we have a move of Y, which is RBX, into T, and T is also RBX. So we'll be able to get rid of this. Then we have a negation of T, which is RBX. Then we have moving of Z into RAX, but Z is RAX, so we'll be able to get rid of that as well. Then we have an add Q of T, which is RBX. Okay? So this right here is the result of doing register allocation. We took our graph, which I'm pointing to off screen right here. Let's just move up. We have our graph of interference relations. We put in all of the registers and give them an initial assignment. We do the coloring algorithm, and whenever we have multiple options, we use the move graph to break ties. Then we take those assignments and then substitute them in, and every time when we're doing substitution, if we see a move from something to itself, we just get rid of it. And so this allows us to remove 1, 2, 3, 4 instructions out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, we remove 4 out of 12, so we improve performance by, 30% or whatever. Obviously, as programs get bigger and more complicated, the benefit of doing this move biasing increases, but also the probability of you even, being able to do it also kind of decreases. All right, I got a little bit of glare there, but now I feel like I'm too dark, so I'm going to turn this light back on. Okay, so that's the algorithm that we're going to do. Now let's actually write down the code for how to do it. So we have our, let me move back. There we go. Okay. We have an interference graph. We have our move graph. Now let's write the algorithm. By the way, there are many register allocation algorithms. There are ones that don't involve graph coloring. There are many graph coloring algorithms. What I'm going to do is I'm going to explain what I believe is the simplest one. Yeah. So this is called the saturation algorithm. And the idea of the saturation algorithm is that we're going to keep track of what edges we are allowed to use. So here's how it's going to work. We're going to write, so our program is going to be called color. And it's going to take a graph. It's going to take an initial mapping of vertices to colors. And it's going to take the move graph. So this graph, by the way, is V and I. So it gets back V and I. And there's a mapping from V to C, which are our initial colors. And then what we're going to do is we're going to return a new mapping from vertices to colors. Now, what you're going to do is you're going to make sure that the vertices already includes all of the registers. So in our example, V is going to include V, W, X, Y, Z, T. Okay, so those are the ones that are things in our program. But it's also going to include all of the registers. So it's going to get RAX, RBX, RCX. It's going to get R11, R12, all of the registers that are available, just everything. And then this mapping, this initial thing, it's going to be equal to, basically it's going to say that RAX is going to go to 0, and RBX is going to go to 1, and so on. Colors, by the way, are just numbers. And so you have all the registers in order, and so because you have them in order, you're just going to assign them initially to whatever their order is. Okay, so that means that what we're really going to focus on is, so we already talked about how to generate V, I, and M, so that's really what the arguments of this thing is, but we're going to generalize it a little bit to take this arbitrary initial coloring. Okay, so here's the algorithm. We're going to start off with W being equal to V. So W is going to start up as V. So that is the vertices of I, i.e. the variables in the program. Okay. Now W is going to basically like a queue. We're going to look through each one. Now what we're going to do is we're going to say, wow, W is not the empty set. We're going to select V from W where the saturation of V is maximal. We're going to define what the saturation is in a moment. Actually, I guess we'll define it right now. So, yeah. So actually, I guess I'll just say what it is. So the saturation of V is all the registers that you're not allowed to use. So in other words, sat V is equal to the color. Okay, so hold on. Yeah, I feel like I need to name these things. So this initial coloring, we're going to call this row 0. So row is going to start off being equal to row 0. Okay, so now the saturation of V is the set row U, where U is in the adjacency set of V. So basically what sat V does is it looks at all of the things that are adjacent to V and then looks up their current coloring inside of row. So basically this first step of the algorithm is that when the queue is not empty, meaning that there are still things to look at, we're going to select from V whatever thing is the most constrained. So think about this in terms of Sudoku. When the board starts, there are some points that have many neighbors that are already assigned. Those are the ones that are the most constrained. We're going to look at those first. Okay, so we're going to look at those first. Okay, so we pick the one that is the most constrained. Obviously, if there's a tie, it doesn't matter which one we do. Then what we do is we select C0, where C0 is the smallest color that is not in the saturation of V. So we have all possible colors, which are, infinity. And we're going to look at the saturation, and we're going to pick whatever the smallest one is. Now, in practice, how do you do this? Basically, what you do is you just look at the number 0, and you say, is 0 in the saturation? And if it is, then you go to 1. And if it isn't, then you choose 0. Okay, but now how do we introduce the move biasing? So with move biasing, what we do, you can think of it like this. What order are you going to look through the numbers in? What you're going to do is you're going to first look through, inside of M, what is adjacent to V. Then you're going to look from 0 up to infinity. So you look at the things that are adjacent, and you see, are they in the saturation? And if they are, then you don't use that one. And if they aren't in the saturation, then you use it. And then once you look through all of the things that are in the move graph, then you look at 0, 1, 2, 3, 4, 5, etc., and infinity. And this will finish, and the reason it'll finish, of course, is because there are a finite number of vertices, and we know that we can color any graph by using a number of colors equal to the number of vertices. Then what we do is we set row of V equal to C0, and we remove V from W. And then that's it. And then row is our answer. Okay. So let's do this algorithm again, but this time we'll use the algorithm precisely. So let me highlight this again. Copy that. Paste it down here. I'm going to move the camera in just 1 second. Okay. There we go. Okay, actually, let me erase first. So I'm gonna erase the previous assignments. So I'm gonna erase that, 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 this one, this one. Okay. So this right here is the input to the algorithm. These are the vertices V, all of them. These edges are I, these edges are M, and then this 0, 1, 2, 3, that's the initial coloring C. Okay, so now what we're going to do is we select the vertex where SAT is maximal. In that case, that is T. The reason that we know it's T is because the saturation is how many things it's not allowed to be, and so T is the thing that is most constrained. Then what we do is we pick the smallest value that we're allowed to choose by first looking at things that are in M first. I'm pointing off screen here. Let me just move this up just a tiny bit. Okay. So we select the smallest one. So we first look through M, but T is only connected to Y, and Y isn't assigned yet, so that means that there's nothing to look at. So then we look at 0, we can't use 0, so then we choose 1, and that's it. Now the next most constrained thing is Z. And so since it's the most constrained thing, we first look through all the things that is on the move graph, and it is connected to X and RAX. X is unassigned, but RAX is, so we choose its color first, which is 0. We check to see if it's in the saturation. It's not, so we choose 0. Now we look at the next most constrained thing. Well, W and Y are equally most constrained, so we choose them in a random way, and we choose Y. So we look at the things that are in the move graph, and it is connected to T and X. X is unassigned, but T is, so we look at 1. 1 is not in the saturation, so we choose it. Okay, now what is the most constrained? Well, notice that W is the most constrained because it is not allowed to be 0 or 1. So we look at what it's connected to in the move graph, which is nothing. And so then we look at 0, can't use it, 1 can't use it, so we choose 2. There we go, 2. Now what's the most constrained? Well, actually X is the most constrained because it's not allowed to be 1 or 2. So we look at X in the move graph. It is connected to Z, which has a 0. We try 0. We're allowed to use it, so we assign it. The next most constrained thing is V. So we look at it in the move graph. It's connected to X. We try 0. It's not in the saturation, so we're good to go. Boom, we're done. And notice that we got the same assignment as before, and the reason we got that assignment is because we chose Y randomly. Okay, so now what do we do? Well, now all we need to do is we need to take this coloring result and actually apply it to our program to be able to do this. And that's what we'll talk about next time.